So just as I mentioned already, homework 8 is due on Tuesday. Also, so what should you work on during the break, just so you don't get, withdrawal symptoms from missing too much hydraulic engineering? Work on the homework, and then also you can begin on the next phase of the design project. Even before you get the feedback from me, you can still lay out where the pipes go. You'll be adjusting the pipe sizes maybe, depending on when I tell you to bring flow rates up or bring flow rates down. But a lot of the design is just putting in the points, typing in the elevations, and so you can do all that now, even before you hear back from me on demand estimation. All right, so this is an image that shows the underground environment. This is actually looking up at the pipes which are buried underground. And when you design a distribution network, you've got one chance to get it right, because you're tearing up roads, and it's very disruptive to ordinary life if you have to go in and replace a main water line. And so it's important that they be big enough to carry all the flow that's going to be required at the end of the design life. When you're designing a new subdivision, there may only be 1 or 2 houses in that subdivision. And so the first several years, it might be the case that there's a very, very low demand compared to the big pipes that you put to that subdivision. But if you put in small pipes, just because at the beginning there's hardly anyone there, then when they build more and more houses towards the end of that design life, when it's totally built out, they call it the build-out condition, when the area is completely populated, then if the pipes were too small because you were thinking, oh, there's hardly anyone here to begin with, then the pressures would be really, really low during the high demand parts of the day. I mean, that's the relationship, is if you put in a small pipe, then the pressure goes down as the flow rate increases. Because remember, our relationship that defines the change in pressure is the Darcy-Weisbach equation. The Darcy-Weisbach equation says that head loss due to pipe friction is FL_V squared divided by D2G. Or if we write that in terms of flow rate, FL_Q squared divided by D2GA squared. Okay, so H sub F is sort of the currency that you're spending as a designer. You're putting the tank up on the hill, and that tank up on the hill is what pressurizes the network. And so that's the source of your pressure. But where is that pressure going? It's either going into people's pipes in their house, what's left of the pressure, but then between that tank and someone's pipe in their house, you're losing a lot of pressure along the way due to frictional losses. And so if you have a small diameter pipe, then that's going to have a small d, which is in the denominator, and the cross-sectional area will be small. And since both of those are in the denominator of the Darcy-Weisbach equation, that means that you're going to have a lot of head loss. And so all of that energy that you gained by putting the reservoir up on the hill, you'll just be losing it due to losses, and then there won't be enough pressure left at the home. And so people will open up the tap and it'll just be a trickle. Or a firefighter will go to a hydrant and they're burning building, and they'll put in the hoses to try and fill up their truck, and they won't be able to get enough water out. So it's critical that there be enough pressure. What happens when there's not? People get thirsty, the green areas die, a lot of negative consequences. And so remember, the design that you should be counting on is the larger of maximum daily demand plus fire and the maximum hourly demand. And you've already gone through that process of identifying what the design flow rate is, so that when you create your network in water gems, at each of the junctions you're going to specify an outflow. And I'll send an email again that gives you an idea of where you can download the software. The software is installed on the computer out here in the labs, but it's probably best for you just to install it on your own laptop. And I'll send an email after class to everyone reminding you of where you can get the software and the license code and everything. So let me talk a little bit more about the pressure range. Each point in the network, each of the junctions that you're going to be serving should have the pressure between 240 and 850. So You actually get low pressure when there's lots of demand because of the reasons I was talking about earlier. You get low pressure at each of the points when there's the highest flow rate and the highest losses. But overnight, like in the middle of the night, if there just happens to be a period of time when no one is using any water, that's static conditions. And during static conditions, that means there's no head losses through the pipe. And so whatever pressure is being created within the network because of the tank being somewhere up on the hill is going to be in all of the pipes. And so you don't want to go above 850 kilopascal, or that's when valves can start to leak. And one of the locations that are particularly sensitive to high water pressures, people's water heaters. And so you need to, in the second phase of this design project, once you draw all of the pipe networks, evaluate the network at two different conditions. At full design flow rate, and you're going to, during that design flow rate, make sure that the pressures don't go too low. And so like if you've drawn all your pipes and you're telling it, all right, tell me what happens, what are the pressures at each of these points when I've got my flow coming out at the outlets, my maximum design flow. And if you see that one of your junctions has a pressure of like 50 kilopascals, what should you do to the pipe that's connected to that junction? Bigger. If you make it bigger, then what that'll do is it'll slow down the velocity going through the pipe, and then that'll decrease the energy loss through that pipe. And so when your pressures are too low, what that tells you is make a pipe bigger. It doesn't mean you have to make every pipe in the network bigger, but the pipe that's feeding that junction or one upstream of it. And so you're going to be doing this balancing act. It's like a continuous optimization. You know, maybe you can make this pipe a little bit bigger, and then that allows you to make some other pipe upstream a little bit smaller. And so you're going to be trying to find what combination results in the lowest price. And so then the other thing that happens is, let's say that your pressure goes above 850 kilopascal when there's no flow coming out during that static condition. And so what should you do if the pressures are too high during the no flow condition? If you've got too much pressure, what do you do about that? I can see why you'd say that, but during the no flow condition, there's no head loss. And so it doesn't matter if you've got a huge pipe or a small pipe. That's right. That's the only thing you can do, because remember, the pressure is coming from how high on the hill the tank is located. And so what you want to do is you want to have as much pressure as you can at night, but not more than 850. Because the higher up on the hill you put that tank, the more that gives you to use up by having really small pipes. So that's just sort of the optimization that you're going for, is lots of pressure but not too much, and big enough pipes so that you get adequate above 240 kilopascal, but the bigger those pipes are, the more expensive your network is. And I'm going to be looking for evidence of optimization. And I've graded this project enough times that I can sort of look at a network and see if you've gone through the process of just making this pipe bigger, making that one bigger, smaller. And there's an automated tool within WaterGems where you can tell it how much each pipe size costs, and it'll go through and automatically try to minimize the cost. And if you want to figure out that function, you're welcome to use it, but I'm not going to be teaching it to you as like a standard course of the project. It's kind of like an advanced tool, although there have been a handful of students through the years who have used that tool. So that's the next phase of the project, is drawing lines and changing the diameter a bunch of times until you have an inexpensive network. Okay. The map that you can draw on top of is already loaded on MU Online, and so if you go to the website, you can right-click on it and save that as an image file. So maybe when I send you the email that has the instructions on where to get WaterGems, if you don't already have it, I'll also include a brief tutorial for the program, because I think there are a handful of students in here who have never used it before. And so I have a recorded tutorial that just in a couple of minutes refreshes your memory on how to, what to click on and so on. for the program. All right. Any questions about the project? Yeah. Yeah, it does. And so, it'll make it more expensive to put it higher up on the hill and further away from the town, but yeah, that's money well spent. You'll spend a little bit more to get it up on the hill in the pipe length, but then that'll allow you to make all of the sizes in the network within the town so much smaller. But yeah, you do need to consider what's the length between that control junction A and the location of the reservoir. And some students sometimes mistakenly confuse the spring location with the reservoir location. And that weird little symbol in the top left of the map, that's indicating where the spring is. And the spring is just where the water is coming out of the ground. But don't put the reservoir right next to the spring, because that'll actually give you too much pressure. It needs to be somewhere between the spring and A, which is the first place that water comes into the network. I see what you're getting at. There's actually several different ways within water gems to say, here's where the water is coming from. You can tell water gems that the water is coming in through a pump, or there is actually tanks, but the symbol that I think is simplest to use is reservoir. And so you'll click on a location, and then you'll type in the elevation of the reservoir, and what you're telling it is the water surface elevation. And it actually, that water surface elevation won't go up or down in the mind of water gems. It'll just be, that's where the water level is at during this peak design condition. And so you won't actually be telling it how big the tank is in water gems. You'll just be saying there's some infinitely large reservoir that has a water surface elevation of X. And so what you maybe should do is say, well, I assume that the tank is going to go here on the map, and the water level will be maybe 1 meter deep. Worst case scenario is that not only is this the day when there's a fire and everyone's watering their lawns and there's a football game, but also the reservoir is really low, so yeah. No, it magically gets from the spring to the reservoir. And not only that, when we talk about the sizing of the reservoir, phase 3 is how big should the reservoir be. Not only does it magically get from the spring to the reservoir, but also the flow rate from the spring to the reservoir just magically happens to be your average daily flow. So by definition, so that's how we can guarantee that enough water gets to the tank. Jared? It's just a junction. Yeah, and at each of those junctions, the way you specify a demand is in the junction table, it's demand collection. That demand collection column is where you type in an outflow. And if you don't remember exactly, how to click to do that, it'll be in the little summary video that I link to in my upcoming email.
So the water flow going to the reservoir is the average, not.
Yeah. And we'll worry, I'll explain that in more detail during phase 3. Yeah. And the reason why it's the average is because the reservoir goes through a cycle each day of draining and filling. Let's pull up the map.
You said they don't all have to be like closed circuits.
That's true. They don't have to be loops. The map on here is what I'm wondering. No. Okay, here's the map. So I don't care how you get the water to the outlets. You could have it go, you know, from L to I, L to H, L to O. I'd probably dock you on optimization if you did that. You know, try and find whatever route makes it so that it's the lowest amount of pipe length and pipe cost. But your question was, you know, is it just one pipe per outlet? Once the water gets here, you don't have to have another pipe going somewhere else. It's just there's a junction here, and you specified the demand collection, and that's all you're designing is these main trunk lines. I mean, in reality, there will be little secondary lines taking the water from this point to the housing project, for example, but that's not what you're designing. Your design ends at the junction. At least, yeah. Water has to be delivered to M and O. I don't care where it comes from. You can figure out what's the best way to get it there. Whether it, you know, is it going to be something from L, then M, then down to O, or, you know, is there some shorter route? That's up to you. This is the first semester, by the way, that I've given students the flexibility of specifying where the pipes go. In the past, I've just said, here are where the pipes go. Now you tell me the size. But I think this makes it more interesting if, you know, if it's not a boring loop in all the cases. I don't think it'll add that much more time. You just knock out a couple of pipes that would have been there otherwise. You know, from here to here doesn't have to be there, whatever. You can. As long as you're using the same offset at each location, that's fine. So if you use the surface elevation for everyone, that's fine. Or if you want to use 1 meter under the surface elevation, that's fine. But specify in your accompanying calculation and explanation what you did. Okay. Any other questions? I think phase 2 of the project is usually what students enjoy the most, is playing around with the program and trying to see how much cheaper they can get their design than somebody else's. Of course, everyone's is going to be a little bit different because you've got different demands. So don't feel bad if your network costs $300,000 more than someone else, because maybe they have a higher flow rate. But if your network costs more and they have a lower flow rate, yours costs more, and you have a lower flow rate, then that's a bad sign. So, all right. One of the things that is in the textbook is the idea of velocity distribution. There's an equation, an empirical equation, that estimates what that profile looks like. And so let's take a look at this figure and then just discuss it here. What it's showing is that if you graph this equation, the von Karman equation, it estimates that the flow decreases as you get further away from the surface. Remember, it's at the surface of the water where the water is touching the air that the resistance is the lowest. So if we think about some cross-section like this, a rectangular channel, the water that's at the middle of the channel and at the top is the furthest away from these edges that are applying resistance to the flow. So this equation says that if you know some depth d, as they're calling it, the depth of water, and you want to know some velocity at location y, then you're using this ratio of y to d to find out what is the velocity at some distance up from the bottom. So you'll notice in the figure it's saying that y is measured from the bottom up. So the highest velocity will be when y and d are equal, when the location of interest is at the top of the water surface. And so here's a graph of what this function looks like for two different slopes. And so in dark red is a shallower slope, and the light red is a steeper slope. So you'll notice that the high velocity at the top, there's a bigger difference between the velocity at the top and the velocity at the water surface for the higher slope. Now, one kind of weird artifact of this equation is that as you get closer to the bottom, that approximation predicts that the velocity of flow actually goes negative. And so usually this equation is only used to describe the velocity within the top 2/3 of the cross section. The bottom third where the velocities become negative, it's not accurate. Once you have an equation like this, it sort of loses track of the fact that sometimes you can do a physical measurement and get a pretty good idea of what the average velocity is by sticking in a flow meter into the actual physical stream and averaging it. So some of the proposals are that if you take the velocity at a point, like 40% up from the bottom of the channel, so if you had a flow meter and you put it 40% of the way up from the bottom and find the flow there, then that's approximately equal to the average flow for the cross section. And so that's what this is saying, is that the velocity at 4/10 of the depth could be taken as a representation of the velocity across the average. Or another way is if you take the velocity at 2/10 of the way up from the bottom and 80% of the way up from the bottom and average those two together. That's sometimes used as the average velocity. On the subject of averaging, sometimes we have to estimate the average n value for a channel that has a lot of differences. And this is depicting a floodplain where the water levels are high. And that kind of describes Huntington right now and the surrounding area. As you drive along the roads that are adjacent to creeks, you'll notice that water levels are much higher now than they usually are. And so the floodplain, which may have vegetation and obstacles like buildings, cars, tree branches, stumps, and so on, that may have a very high n value because it's more rough and the particle sizes are larger compared to the main channel, which is relatively smooth because it always has water in it that's scouring, and any sort of debris that's been there is washed downstream during a high flow event. So the question is, what do you do when you've got water flowing through this channel and you have some sections that are rough, some sections that are smooth? And there's a number of different equations that have been developed to try and estimate or average what the composite n value is going to be. And one of the commonly used approaches is called the Horton-Einstein method. And what that is it's saying that you weight the perimeter, you do a weighted average based on perimeter. And so you can see that this edge section here, they're calling section 1, then the floodplain, they're labeling section 2, the side slope in the main channel, section 3, and so on. And so in the Horton-Einstein method, what you would do is you would take the length of each of these segments. You'd find the distance from the water surface along this side edge here. You'd find the length of that and multiply it by the n value, and then you'd add it to this length multiplied by the n value and this length multiplied by the n value. That's what is here in the numerator, and in each case you are taking the n value to the 3/2 power, as is indicated here in the numerator. And then in the denominator, it's just you're adding up all of the wetted perimeters, and it's just sort of a way of coming up with a weighted average of the n value. And there's other approaches as well. There's sometimes just a simple average. If you've only got two different n values and relatively the same distance for each, you could just take the simple average of both. But I wanted to make you aware that that's one of the issues that we face, even if it is a regular channel like this. It might be that there are irregularities and differences in the roughness. Okay, so you'll remember here is Manning's equation, and this is where we come up with the idea of taking the cross-sectional area to the 5/3 power. There's area to wetted perimeter. This is the hydraulic radius term to the 2/3 power, and then the area is outside of that as well. So looking at this equation, let's say that you've got some certain n value that corresponds to a material. A typical n value for concrete is 0.013. And let's say that we've got a certain slope that we can't change. And that's usually the case. In hydraulic design, it's not like you can go out and change how steep the earth is. That's usually just something that you're dealing with when you're trying to put in a canal that connects a water source and a water destination. It's just, you know, the slope is going to be whatever the ground slope is, and you can't make it steeper just because you wish it was steeper. So it's a fixed roughness because that depends on what you're making the channel out of. A fixed slope. All you can do as a designer is change the cross section. So how do you maximize the flow rate that you're able to carry? So to maximize the flow rate, let's just say that we're looking at channels like this. What do all of these channels have in common? You got the same area. Yeah. Here you can see this has an area of 20 meters. This is a really tall but skinny channel. This is a little bit wider and not quite as deep. 4 times 5, 5 times 4. So they all have the same cross-sectional area, but how are they different in terms of what we've got here? The wetted perimeter is going to be radically different. Yeah. If we consider this as a wetted perimeter of 22 meters, because we've got 10 on each side and then 2. This, even though it looks like the same shape, it's a long rectangle, it actually has a wetted perimeter of only 14. Okay, here the wetted perimeter would be 8 plus 5, so 13. Here it's going to be 14. So if we have the same cross-sectional area, how can we maximize the flow rate? Look at the equation there. N is fixed, slope is fixed. All 4 of these have the same area. We want to minimize the wetted perimeter. Yeah. So let's do that using a spreadsheet as an example. And the nice thing about a spreadsheet is it gives us the opportunity to play around with numbers really quickly. So let me just fire up a spreadsheet here, and we'll try and find out what's the most efficient cross-section. What's the cross-section that gives us the best flow rate? Okay, so we have n equals 0.013. Our slope, the slope of the water surface of the channel is 0.01. And then what we're going to have here is a variety of different cross-sectional areas. And maybe what we ought to do is have that in terms of the width b, and then we will have the depth y. So for the first one, for example, it had a width of 2 and a depth of 10. So here we can get the area. It'll be just the width times the depth. Oops. Okay. And then we also want to know the hydraulic, the wetted perimeter. So the wetted perimeter is going to be 2 times the depth plus the width. Okay, so we've got the wetted perimeter, the cross-sectional area. So now let's find the flow rate. And that's going to be cubic meters per second. So if we're going to just do Manning's equation here, let me copy that over. Okay, so Q is going to be 1 divided by N. I'm going to anchor that so that when I move around it's always referring to the same location for N. Times the area to the 5/3 power. So here's my area to the power of 5/3. Divided by the wetted perimeter to the power of 2/3. And then times the slope. I'm going to anchor that as well because I don't want it to move around as I try different combinations. Something's not right here. Let's see. Oh, slope. That's right. Thank you. To the 0.5 power. There we go. Thanks for catching that. All right, so we've got Manning's equation here. So we've had our first one, then this was 2 by 10. So it was 10 was the width, 2 was the depth, and then we can just copy this over and it does the area and wetted perimeter and the flow rate. So which is going to carry more flow? According to Manning's equation, we're going to get more flow through the second one. So you're thinking conceptually, why should we get more flow through this channel than through this one? So you were making this gesture. That gesture is referring to like the effect of the sides, right? Right. So if you look, like where is the water? How far is the water away from where resistance is being imparted? You know, this flow area, it can never get away from the resistance. You know, even when it's in the very middle of the channel, it's really close to this side or it's really close to that side. And in both cases, the flow is under the influence of this roughness element that it is applying a shear stress. Whereas, compare it to here, even though it is under the influence of the bottom, it's far away from the edges. And that's what's accounted for by the ratio of the area to the wetted perimeter. When you minimize the wetted perimeter, you're sort of saying that you get more flow by minimizing contact with the location where shear stress is applied. Okay, so let's try some of these other combinations. So we had one where the width was 5 and one where it was 4. And so then here it was 4 and this one was 5. Okay, so let's see what that does. We will just drag everything over. Okay. So it seems like of the options we've tried, the 4 depth and 5 width is the best. So this one is the best of the 4 options, but how could we find out what's the best combination? We're using Excel, so we've got a lot of tools available. Well, what I want to do is I want to have the biggest flow rate possible. And so let's call this one best. How do we make it the best? Well, we know that in the best, all of these had an area of 20. So the area has to be 20 or else it's not a fair comparison. The wetted perimeter, that's going to be whatever the area is. I'm sorry, no. The wetted perimeter formula is going to be the 2 times the depth plus the width. We don't know what to use yet, but the width and depth are going to be related to each other because together they have to equal 20. And so we'll just say, what if the width is 3, then the depth has to be the area divided by 3, whatever's in that location. So now I'm going to play around with this channel width, 3.2 and so on. So here is my flow rate. Okay, so what I'm going to do is by changing around B, I can find out what gives me the best flow rate. So is it 5? 5's pretty good, 205. What about 5.1? Is that better? 5, yep, 5.1's even better. So the automated way to do this, you know, we've been using GoalSeek. Solver is the stronger of the two. So the problem with GoalSeek is that you have to know what you're looking for, what value you're looking for. So I could tell the program, yeah, change that one. No, okay. We would want to change this to what gives it 200 by changing that. So we could tell, as long as we know what flow rate we're going for, it'll calculate the dimensions that give you that flow rate. But we don't know what the upper limit is. Like, well, okay, tell me what is the dimensions that gives me, what if I want this to be 500 cubic meters per second? I want it to be 500. So do that by changing this. Bless its little heart. It's trying so hard, but it couldn't find it. It tried hundreds of times, but it never found the value that gave me the flow rate I was looking for. So that's the limitation of goal-seek, is it has to have the actual goal. Solver, on the other hand, you can give it a criteria like maximize. And so that's what we want to do. We want to maximize. So we want this flow rate to be maximized by changing this. This has always been the parameter we gave it permission to change, but now we're saying maximize the flow rate and then solve. And apparently it did that. It found that the best dimensions here is to have 6.3 for the channel width and 3.16 for the depth. So we'll remember that. It looks like it's saying have it be twice as wide as it is deep. Twice as wide as it is deep. Now, it turns out that we don't get that much more flow, right? We went from 205 to 208. So it's not that big of an increase, but you know, every little bit helps. So what we learn is that the most efficient cross-section in the case of a rectangle is that it should be twice as wide as it is deep. Here's the most efficient trapezoidal channel. So the most efficient trapezoidal channel actually should have side slopes that are pretty steep. This square root of 3 divided by 3, is that 0.7? Anyone with a calculator tell me what's the square root of 3 divided by 3? The square root. Oh, 0.5, yeah, 0.58. So what it's saying is that the horizontal component of that slope should be less than 1. And so that's actually a pretty steep side slope that you wouldn't be able to achieve with like a soil. You could achieve a steep side slope with concrete or with rock, but you know, just from the dimensional standpoint, what is the channel that conveys the most flow for a given cross-sectional area? It should be a shape like that has these dimensions, where the wetted perimeter is 2 root 3 times the depth, and so on. What it turns out to look like is it's the nearest approximation to a circle that you can get with a trapezoid, where what you're doing here in this shape is you're maximizing the area and minimizing the wetted perimeter. You're trying to get as low as possible for the wetted perimeter. The thing about it is that the hydraulic radius is just the depth divided by 2 for this best trapezoidal channel. Here is a table that shows for different types of shapes what's the most efficient channel. So if we go back to the rectangle, you know, the example we did with Excel, we found that the width, B, should be double the depth. That's what this showed when we ran the solver, is we said that the width should be 2 times y, the depth. And according to this table, it's showing the same thing, that for a rectangle, the most efficient channel is a half square, where B is 2 times y. So, why don't you try your hand at this? Calculate, using this example, the flow depth that gives you the best triangular section, where the flow rate's 2.5 cubic meters per second. Here's the end value and a slope. What flow depth should be used for that triangle? You'll need to put it into Mannings equation and solve for y. So if we were actually building a channel to carry this much flow, one other thing I'll mention before we finish is that usually you add a little bit of additional headroom above where the water surface is going to be. That's called freeboard. And the freeboard is just sort of a safety factor in case it's windy and there might be some waves, or if the flow is a little bit higher than expected, or if flow is going around a turn, actually the water level will rise on the outside edge of the curve, and that's a phenomenon known as super elevation, when water is going around a bend. And so there are some guidelines that say how much freeboard you should put into an open channel, and we'll talk about those guidelines towards the end of the semester when we get into design constraints. All right, well, let's just double check these announcements. Remember that there's no class next week because of spring break. Don't be here because I won't be here. But we will get back together on Tuesday the 24th, and that day you're going to submit a homework. And if you've got any questions about the project between now and then, I'd be more than happy to try and help you. Look for an email from me within the next hour or so that has all the information that you'll need about water gems. So have a good vacation, and I'll see you on the 24th.